Hello, everybody. Welcome. I would like to speak about the Glassy carbon. This presentation is actually, I do thanks a lot to Brent, Boode, who was a PhD at work on this project under my supervisions. And we discuss here about Glassy carbon. First of all, I would like to introduce a bit about myself and my research group. We are the West Center for Printing and Coating. We have been existing for over 30 years, from 1990s. We are dedicated to the development of printing, especially as an advanced manufacturing process, study the science of printing, applying printing in all the main areas, graphics, print electronics, biomedics, and energy storage, to provide a solution to industry and collaborate extensively with industry. In the last 5 years, for example, we've done a lot of range of projects of different natures. What is, I think, I love is the variety of applications where we apply our expertise in printing technologies. Every 6 months, new projects come up with different challenges and requirements. And that is beautiful. But the advantage also to work in academia is sometimes you can work on weird stuff, more rare stuff. And one of these materials is, of course, all supported by world-class facilities, from small scale to large scales. Now, one of the nice materials that I studied as a student, this was an IEEE granted, so Research Council project, was about glassy carbon. So we all talk about carbons. People know graphene. People know very well activated carbons, graphite. What is glassy carbon? It's a non-graphitizing forms of carbon that combine together the glassy and ceramic properties with properties like conductivity, typically of a graphite. Glassy carbon, for example, is extensively used in electrochemistry. Why? Because it's chemically resilient and is inert to chemical reactions, has very good electrical conductivity, and has very wide electrochemical voltage potential windows. So it's fantastic for multiple applications, and is thermally stable at high temperature. It's a great material. So why we don't speak about this one more in energy storage and in print electronic? One of the challenges is how to manufacture glassy carbon, and in particular, how to manufacture thin films of glassy carbon that can be used in printed electronic, particularly. Why is difficult, this one? The conventional pyrolysis process, the conventional process, is long. You take a phenolic precursor and you treat it for 10 hours at over 800 degrees. You understand the process is very demanding. It is anyway an important and valuable process. So part of our research was to work to deposit thin layer phenolic precursors and pyrolyze it and transform it into glassy carbons. And here are some of our some examples. This is glassy carbon, 2-3 micron thick, deposited and printed over stainless steels. This is an example and was an interesting process to optimize. Area of application of this one, energy storage. Glassy carbon, very good barriers to chemical reactions and oxidation and other phenomena. But what is the beauty of research? It's exploring strange new alternatives. So what we've been working is a new way, a new approach to generate glassy carbons. This was published in 2022, and it makes use of photonic curing. We use photonic curing for transforming the cured phenolic resin into glassy carbon. What is photonic curing? Photonic curing is essentially a cell lamp, very, very bright, that flash very quickly. We speak about hundreds of times per second, producing and releasing a lot of energy in a short amount of time. And you can tune the frequency and the intensity. And through an extensive work, you can see in the articles, different options, we were able to reduce the time required for converting this thin layer of phenolic resins into glassy carbon from the thermal transformation of 10 hours in less than 1 minute. That's the power of radiation. Lots of energy in a very short amount of time. Another advantage, what is it? You are hitting only the top surface. You are not hitting the substrate underneath. This means that the supporting substrate is subject to lower temperature. You don't have to heat up to 800 degrees for 10 hours. So you can use also more thermally sensitive materials. Of course, These are nice presentations, nice pictures. We try to be scientists, but we have to verify what we produce. So yes, Raman, XPS, SEM, compare throughout. And the key point that Raman was demonstrating, we hit exactly the same peaks. We know therefore that conventional, our advanced conventional, and the proposed full nova photonic curing generate glassy carbon. So we have two approaches now presented for glassy manufacturers: enhanced thermal process for thin coatings, thermal, and a novel photonic curing. And then we can move now to printed electronic. Fantastic. Main area of application of glassy carbon I mentioned is energy storage. Energy storage does not need patterning. What we do is lock down by coating. We coat large area of substrate that act as electrode. And these are fully coated 100%. So for process like this one, we can use element like in lab, like bar coating, or in industry, element like slot die coating. What can we do instead when we want patterning? And of course, we first actions, the workhorse of printed electronics is screen printing. That's a nice process, very flexible, a good workhorse. So let's try to screen print and use screen printing as a pattern. The important point, what is it in all this? Control the deposited thickness of your materials. You want the deposited thickness to be highly controlled and uniform across the board. Good. So we develop, especially Brent student, a lot of work and processing to improve screen printing of the glassy carbon, of the precursor resins. That is screen examples, an example of cured resins, and on the right, an example of carbon cured resins. Key point here was, before printing, assessing the rheology. As a center of research, we love rheology, because by understanding how fluid flow and wetting property, we understand how we'll print, and assessing also other parameters, health and safety, very important, especially when you work with phenolic material. That's absolutely priority. So with the position by screen printing, we thermal cured, and we print a lot of little examples. So of course, we started work also printed electronic. There was some discussion yesterday about impedance of element. The key point when we discuss about printed electronic, people is always interested about conductivity. So what happens if we print some tracks? Well, we printed by screen printing some tracks, and we assess what we obtain. And we were very pleased. Very consistent thickness, 2.5 microns, 0.2 standard deviation, very consistent and very low resistivity. In fact, when we convert to the commonly adopted sheet resistance optimized at 25 micron, we got a resistance of 8 ohms per square. Now, what is interesting here? Glassy carbon is also isotropic. So it's not in one direction only that is conducting in this way. It's uniform property in these directions. So we achieve a very good conductivity, a very good low resistance of our materials, equivalent to very good graphitic inks. And what is another advantage? Once Q and sintered was extremely scratch and wear resistant. We break first the substrate, that was alumina, then our glassy ceramic carbon. Fantastic. We demonstrate now some printed tracks, and of course we want to select some demonstrators. And one element of interest is to see how glassy carbon perform as a temperature sensor. Why? Because it could be used at different condition temperature. Key point of glassy carbon, you can achieve a very high temperature. It's a no graphitizing form of carbon. That means that when it's formed, it doesn't change with temperature. Great. Test. Of course, our oven reaches only 140 if you want to test properly and precisely. So there's a limit. So we test from 20 to 140 degrees. And what do we find out in this testing? First, we find out that all the samples tested were extremely consistent among each other. There was a very excellent, strong linear correlation temperature versus resistance, with also a specificity with a response of 0.0021 ohms over ohms degree, with a very small error in standard deviations. The standard deviation there is not across the entire samples tested, the range of samples, the 4 samples tested. Interesting point in this one, how does it compare with other commercial sensors in terms of specificity, of sensitivity, and in terms of cost? Usually we use tungsten sensors, platinum sensors, PT100, and these has a very similar absolute value of correlations, 0.035. In the case of metal, the response is positive. In the case of carbon, as well known, the response is negative. So there is a decrease of resistance with the temperature. Key point also, that I stress again, is how resilient is this coating. Of course, here I present about the sensors, but the key point, what is our vision and long-term point, is not only temperature sensors. Key area of interest, what is it? Development of printed circuits. And in this sense, there is a challenge. You spoke before about low temperature bonding. One possible potential is higher temperature bonding with glassy carbon. Electrochemical cells. This project was born studying batteries, supercapacitors. Key point application for us for glassy carbon is to create protective coatings to be adopted with more nasty electrochemistry. And then, of course, we have some investigating intelligent sensors for multiple applications in this area. So what I want to finish here to discuss, in fact, the time is running, 12 minutes. Glassy carbon. Quote was the key point of this presentation. We are working essentially to try to unlock the potential of glassy carbon. I present briefly 2 manufacturing approach: thermal convention, enhanced for thin films, and a novel photonic curing. There is new opportunity for glassy carbon as interesting material for print electronics. I showcase an example of temperature sensors. Next scale, what is it? Large scale. Working with industry to make it large scale optimizations. Well, and to finish off, acknowledgements. Aside Brent, we have to thank the entire group of WCPC. We are based in that beautiful Bay campus in Swansea. And of course, we have to thank also the research councils that funded the PhD of Brent.
Thank you, Davide.